In this video, I'll demonstrate how to build a 12 volt generator, just like this, from easily accessible parts, most of which you can get for free. It's a video meant for beginners, so I'll demonstrate the build process as well as go through the basics of how and why it works. Let's get started. Here's the part where I talk about how and why it works. Please note how this video is split into different chapters. You can easily skip this part if you know all you need to know about electromagnetic induction. A generator creates electricity from a mechanical motion, in this case of our generator, the turning of the gears and rotor across the stator. When we say we create electricity, it sort of implies that we create something where before there was nothing. But all we really do is turn one kind of energy into another. All energy in the universe was created at the time of creation, and all we've done ever since, and probably ever will do, is turn one kind of energy into another kind. In this case, we turn our physical input into an electric output, so we can also think of a generator as an energy translator, in much the same way as a motor translates electrical energy into movement. We can never get more energy output than what we put in. That's just the way the laws of physics govern. We can only try to minimize the energy loss in the generator between the input and the output, and there will always be some energy loss. Again, the laws of physics at work. The forces at play in converting our physical movement into electricity is known as electromagnetism, and it's one of 4 fundamental forces of nature that govern how the entire universe works. You have the strong force that determines how fundamental particles in atoms are bound together, or the weak force that determines how they decay in microseconds or millennia. And of course, we have gravity that dictates how everything else aligns together, from vast galaxies to apples falling from trees. And then you have electromagnetism that basically governs how everything else interacts. The principle we're most interested in, generator-wise, is known as electromagnetic induction. Electromagnetic induction works by creating a changing magnetic field around an electric conductor. The easiest way to demonstrate this is by moving a magnet back and forth across a wire coil. Inside the wire we'll have a bunch of atoms, and these atoms have a core, a nucleus it's called, and this nucleus have a bunch of electrons that whirl around it, and this creates a tiny magnetic field. You don't intrinsically get electricity from just the wire itself, because the electrons spin in random directions and their magnetic forces cancel each other out. So until a magnet comes along, it's just a boring coil. Magnets have their molecules arranged so that their electrons spin in the same direction. This creates a uniform magnetic field, and when we move a magnet across a wire, all those electrons in the magnet will push or induce, if you will, the electrons in the wire to move in the way of the magnet. Some of those electrons will be pushed loose from the atoms, and it's this displacement of all those free-roaming electrons that ultimately creates the electricity. All this is vastly simplified, of course, but that's basically the idea. A bunch of magnets on the generator rotor, that is the part that rotates, move in and out of the coils on the stator, that is the part that remains stationary, and electricity is the result. The more powerful the magnets and the more and stronger wire coils you have, the more electricity we can produce. And now let's continue to build our generator so we can provoke electromagnetic induction and make our own electricity. First, the parts. 3D printed gears. 6 of them are so-called compound gears, which mean they're actually 2 gears joined together, a small one and a big one. Each gear needs 2 bearings, Later in the video I'll show how to get these for cheap or even free. One initial gear is not a compound gear, it's just a single spur gear. This one doesn't need a bearing. Instead there's room for a hex nut, an M8 hex nut to be exact, in the middle of it. This gear is the one that sets all the other gears into motion, and it's set with a hex nut in the middle so as to hold tight onto the bolt that makes up one of the two shafts of the gearbox. You'll get the idea later on when we assemble it, but basically I'm using bolts that aren't fully threaded to stop the hex nut from traveling too far up the bolt. And the reason why I do this is because this gear needs to be fixed to the shaft, and this is usually done by drilling through the shaft and inserting a pin through it. But that's just very hard to do precisely if you don't have access to a decent stationary drill press. But most people don't, and it can be difficult and error-prone process. So this is an easy way to avoid that problem altogether. 5 M8 times 130 millimeter partially threaded bolts. To be exact, they should be quarter threaded, meaning 28 to 30 millimeters of thread on the bolt. These should be readily available at your local hardware store. An 8 millimeter push rod will do just as well. I'll try to leave a link in the description. It's actually just one partially threaded bolt or push rod we need for attaching the initial gear. You can use cheap and regular M8 threaded rods for the other shafts. 130 millimeter push rods will work as well, but the 30 millimeter thread is a requirement, as we'll later see why. What else we need? 2 3D printed end plates with bearings, 1 3D printed rotor also with bearings, magnets for the rotor. I use neodymium N52 magnets 20 times 3 millimeter. I'll leave a link in the description below. If you have stronger magnets lying about, you can easily copy the TinkerCad design in the description and incorporate these into your design instead. I'm afraid magnets aren't cheap, but they're pretty indispensable in a permanent magnet generator such as this. The way I designed the rotor means the magnets can be easily extracted for other projects. They aren't glued down or anything, so that's a consolation at least. You need 8 magnets. An 8 millimeter shaft for the rotor. It's not important that it's aluminium, as is seen here. That's just what I had lying around. The important thing is that it's not metal that's too heavily attracted to the magnets nearby. It'll just slow the rotor down. You can 3D print an 8 millimeter shaft if you like. There's one in the TinkerCad design. 1 stator 3D printed, also with bearings. 6 3D printed caps to hold the coils in place into the stator. Copper wire or magnet wire for the coils in the stator. Also not cheap, but you can do what I do and source the copper wire from broken household equipment such as discarded microwave ovens and such, as I'll show you later on. Crazy glue to tie down the coils as you wind them. 6 coil cores to wind the copper wire around. These can be 3D printed. The model is in the TinkerCad design in the description. The ones you see here are some I took from an old pair of rollerblades. More on that later. And a bunch of 3D printed spacers. And that's about it. A soldering iron isn't strictly necessary, but if you do have one, it's a good idea to make use of it when it's time to make the stator. Now on to the 3D printing. The generator is designed in TinkerCad and it's available for free in the description. Don't fret if TinkerCad is something you haven't tried before. You don't have to know how to use it to print the design. Simply click on one of the elements and press the export button in the top right corner. Then proceed to select the STL format that your 3D printer software, or slicer as it's known, will know how to process into something your printer will be able to print. Then just print away. I'm using the Ender 2 Pro here, which is a mini desktop printer with a not very large build volume, but the design will fit into it without problem. It's a great printer, it's dead simple to use and has never failed me. I highly recommend it. One thing to note is that I deliberately made the fit for the bearings very snug, so they will stay put. This means that you have to apply some pressure to get the bearings in there. I recommend using a vise, but if you don't have one, you can just as easily hammer the bearings into place. Just use a piece of wood and don't hammer on the bearings directly. Same thing with the hex nut for the initial gear. It's a deliberately tight fit. About those bearings, let's quickly go over a great method for getting them for free. The bearings we need are 608cc bearings at 22mm diameter. Pretty standard stuff, and if you happen to come across a pair of discarded roller blades, I've found these to be an excellent source of bearings. For this set of roller blades I get 16 excellent bearings. It doesn't get much cheaper than free. I also get these metal spacers. These will come in very handy when it's time to wind the coils of the stator, as I'll later demonstrate. Copper wire, or magnet wire as it's also called, is very easy to get hold of. Discarded appliances are usually a great source of the stuff, such as this discarded microwave oven, for example. Although the motor is shot on this one, there's still a load of useful parts we can source for our projects, copper wire being just one of them. Looks like 0.1mm wire, probably 50 or 70 feet of it, all from just the oven fan. If you haven't handled copper wire before, you are perhaps wary of breaking it, but there's no need to be overly concerned. It's quite durable, and the enamel coating that acts as insulation doesn't easily come off. Such is the state of the world that we throw away too much stuff that could otherwise be easily reused. Take this component board with its relays and capacitors and whatnot, all likely in good working order. I encourage everyone to reuse and recycle whenever possible, but that's a sermon for another day. For now, let's put the copper to use and wind some coils. We'll use the 3D printed caps from the TinkerCad design. They fit right into the stator, as we'll see later. But we need a core that we can wrap the copper wire around. I got these metal ones from the pair of rollerblades I took apart, but rest assured there's a 3D model of these cores also in the TinkerCad design, so you can just 3D print them if you don't have a pair of rollerblades to dismantle. Just be aware of the important difference between a metal and a plastic core. The metal core will generate much more electricity, but make it harder to rotate the gears because the metal slows down the magnets. The plastic core will generate less electricity, but the generator will be very easy to rotate because there's no metal to interfere with the magnets. With the core in place into the cap, we can roll the wire around it, but we need a backstop of sorts so the wire won't fly away from the coil as we roll it. I mount the coil on one of the black socket screws I got from the rollerblades, but you can use any kind of rod or bolt that will fit. Then I use a washer as a backstop, as tight a fit as you can find. I tape it up beforehand. This makes it easier to reuse it with the other coils you need to make. Then we fix it into place, ready for winding. We need a bit of loose wire for our stator later on, so allow for a few inches of copper. Fix the loose end to the mount with a bit of duct tape or similar. And then we wind away. 50 turns of wire with each iteration, and with 0.1mm wire we need 400 turns in total, or as many as you can fit inside the cap. Don't wind beyond the cap's boundaries or you won't be able to fit it into the stator. After every 50 turns I pause and write down the total number of turns. because I get easily distracted and don't want to lose count. Then I apply super glue or crazy glue to the coil to hold it together. Careful you don't glue your fingers together. For the sake of argument, let's just pretend I never did that. And so we wind and we wind and we wind and glue and wind again. And in the end, you'll get the 400 turns down, and we can fix the end of the coil with a bit of duct tape and wait for it to dry. When the glue has settled, we can take it apart. It does take a bit of force, but it should come off, and you should end up with a coil that looks similar to this one. It is not unreasonable to expect to have to do a bit of experimenting with the coil winding. Maybe your setup likely it won't be exactly like what I have here, but that's not terribly important. We just need to get as many turns of copper in as possible, and you need to wire the same number of turns with each coil. So we have the coils and we have the stator. Now, by way of the design, the coils are meant to be inserted into the stator. If you look closely, you can see the flange on the cap. It should fit right into the stator body and click into place. Now it's time to connect the coils together. We can't connect the coils just like they are because the copper wire is insulated. To be more precise, it's actually coated with a form of varnish. The coating is very thin, but we need to get rid of it to get to the actual wire beneath it so we can connect the coils. The trick to get rid of the insulation is to simply burn it away. A lighter should do fine. Just hold it to the tip of the wire and the insulation vanishes. You're left with a bit of black stuff. You can use your fingertips to get rid of some of it, but the rest will have to be sandpapered away. Gently apply the sandpaper to the tips. Use as fine-grained sandpaper as you can find, and only move the sandpaper away from the wire. Going back and forth, as you would normally do with other tougher materials, will likely damage or even break the wire. Beneath the insulation, the copper wire will appear, a strand of wire much brighter than the coating. It's difficult to show it here because the wire is so thin, but you will be easily able to recognize it when you have a go at it yourself. Remember to cover all the sides of the wire. You want as much copper exposed as possible to get a good connection. The magnets will rotate around the surface of the stator and excite the coils, inducing electricity. We just need to figure out the best way to extract it. We could connect all the coils in series from one to the next all the way around. That's known as a single-phase generator, but it's also not the most efficient way of going about it. What we'll do instead is wire the opposite coils in series. As there are 6 coils, we get 3 series or phases. Indeed, this makes the generator a so-called 3-phase generator. It's a more efficient way of generating electricity, and indeed the 3-phase generator is the workhorse of the modern power generation arena. So we'll do the following. Leave one end of the coil sticking away from the generator. This we consider the start wire of the coil. Locate the other end. This is the end wire. This end wire must be connected to the start wire of the coil exactly opposite, and the end wire of that opposite coil should stick away from the stator. You decide for yourself which wire of the opposite coil will be your start wire and end wire. That's not terribly important. Having located the end wire of coil 1 and start wire of coil 2, we join them together. Simply twist the end parts around each other. If you were diligent with the sandpaper, the copper inside the insulation will have been exposed and electricity will flow between the 2 coils as their wires make contact. Because I have a soldering iron, I will solder this connection tight, as I have with the connections you can see here already prepared. It's not strictly necessary to solder the connection for the generator to work, but it'll make for a much sturdier connection, so I recommend it. I know it can be difficult to see here in the video, so I'll refer to this image for clarification on how to wire the stator up. I color-coded the three individual phases. The only thing to note is that we have to connect coils opposite each other. We can't connect them side by side. This is a good time to test the connection. If you have a power supply or battery, you can test it through the coils to a measuring device or small LED light or similar. So we now have 3 individual phases, but we still need to connect those together. We do this by connecting the 3 start wires together, leaving only the 3 end wires exposed. Again, somewhat difficult to see on the video, so I'll refer to another image. You can determine yourself which wires will be the start wires and which will be the end wires, as now we have 6 coils with 6 wires sticking out. Simply pick 3 wires side by side and join them together. And there's the finished stator. The magnets will whirl around the coils and induce electricity, in effect creating 3 different streams, if you will, of alternating current. The coils do seem rather exposed, and there's a risk they could be knocked out of their sockets by the fast spinning magnets. To alleviate that risk, I wrap the front of the stator with clear packaging tape. It takes a bit of work with the scissor or Stanley knife, and one must be careful to not damage the coil wires, but it's worth doing. And that's it for the stator. Now on to the rotor. Contrary to the stator assembly, the rotor is much easier to put together. I designed it so that the magnets can simply be pressed into place. Apply a bit of force and they pop right in and stay there. These are neodymium N52 20x3mm magnets, and I specifically designed based on these ones. If you have other sizes, you can adapt the TinkerCad design to fit your ones, if you have knowledge of how TinkerCad works, that is. The only important thing to note here is that you absolutely must insert the magnets in reverse polarity order. First, add a magnet with its north pole facing upwards, then the magnet beside it must have its south pole facing upwards, and so on and so forth. If you don't do this, the magnets will not induce sufficient alternating current into the coils, and you won't get much electricity flowing. I recommend adding 1 magnet at a time and testing the polarity of it to the magnet next to it. If they repel each other, you have the direction right and can continue to press it into place. If they attract each other, you must turn it over, make sure they repel each other, and then insert it. Then just keep going until all the magnets are done. Then you can test with a smaller magnet if you have one. Each magnet on the rotor should alternate between attracting and repelling it. If you got one wrong, simply pop it out and turn it over and put it back in. And that's our rotor done. All parts are now in place, so we can assemble the generator. And here are our parts. First off, we secure 2 bolts to one of the end plates. Place 2 washers on each of the bolts before passing it through the center bearings. Then place 5 washers on each bolt in preparation for the stator. Then add the stator through the center bearings. The coils should face inwards, not outwards. Fix the stator in place with the aluminum rod or a 3D printed plastic rod if you don't have an aluminum one. Add 1 washer, then the rotor. If the cores of your coils are metal, you'll feel the rotor magnets adhere to the stator. The rotor should spin freely no matter if the core of the coils is metal or plastic. Now more washers. Add 3 washers to the bolt where you want the first gear to engage the rotor. Then slide the gear into place. 1 turn of that gear equals 1 turn of the rotor. We say it has a 1-to-1 gear ratio. Add 6 washers to the adjacent bolt and 1 more gear. One turn of the second gear will turn the rotor 2 times. We say it has a 1-to-2 gear ratio. Keep adding gears with a single washer in between. As you add more gears, the rotor will double in speed for every gear added, as the gear ratio becomes 1:4, then 1:8, and so on. A fast rotor yields more electricity, but it also comes as a cost. We can't just keep adding gears, because the more we add, the more power is required for them to turn. With each gear doubling the gear ratio, that quickly adds up, and soon we won't be able to turn the gears at all. With 3 gears on each side, it's time to add the fixed gear. You should have a 3D printed gear with a fixed hex nut pushed into it. Rotate it on the bolt until you can't rotate it any further, because another gear will be in the way. Not a problem. Simply turn the bolt instead of the gear, and you'll be able to slowly mesh it into place. That's it for all the gears. Add 2 final washers and place the second end plate. Then slide the aluminum rod into place. It can't be a tight fit. Make sure to take your time. All the gears should spin freely. If they don't, trace back and make sure they do before closing up with 2 hex nuts on each end of the bolts. Allow for a bit of space between the end plate and the hex nuts. You mustn't tighten the nuts into the bearing of the end plate. That's the bulk of the generator. All that's left now is to stabilize the device with the 3 remaining bolts or push rods. Push or screw them into place and fix with hex nuts. And that's it. The generator is complete. With a bit of effort, you can turn all the gears by hand. Notice how a fraction of a turn of the hex nut gear results in many turns of the rotor because of our gear train. Let's test it out and see what it can deliver. Here is the generator ready for testing. The activation is simple. Just turn the drive bolt with a ratchet or wrench. You have to spin away from the generator because of the way the hex nut gear is applied to the bolt. If you spin it the other way, the gear will come loose and travel away. Just rotate it back into place. As we rotate the bolt, the gears will spin and turn the rotor, generating electricity across the stator. Specifically, we get the aforementioned 3 streams of alternating current, each stream exiting from each exposed coil wire strand. We need to convert these 3 streams of alternating current to 1 stream of direct current in order to drive anything useful. What we need here is a so-called rectifier, like the one I show here. We have 3 input lines for our 3 alternating current streams and 2 output lines for a plus and a minus pole of direct current or DC. Let's hook it up. The order of the connection isn't important. Just pick a wire and go from there. We'll hook up the direct current plus and minus to a voltmeter so we can get a reading. Let's see what kind of voltage the generator will deliver. Hold the generator down while turning it. The force is strong with this one. 4 volts, 8 volts, 10, 12. We peak at 12.11 volts. That's not too bad for very little physical effort. But volts only tell half the story. We need to measure current, or amperes as it's called, to see how much the generator delivers in terms of power. If you're unfamiliar with volts or amps, there's a great beginner's analogy in how water flows through a pipe. Think of volts as the pressure of the water through the pipe. 12 volts of pressure will line up with electronics that need at least that kind of pressure to function, like a fan or phone charger. But we need those volts flowing through the wires, and that flow is measured in amperes or amps. So if volts can be considered the pressure, amps can be considered the flow rate. Let's hook up the voltmeter to measure amps. We'll send the power through the meter to a small 12 volts fan so we can measure the current or the amps going to it. We get about 100 milliamps. Remember, we're translating energy into electricity, not creating it out of thin air. So that is really as much as we can reasonably expect from our measly physical effort, and this current generator design at least. The trick is, of course, to drive the generator from wind or water, so we don't have to drive it by hand. All's good. The generator works as expected. Time for some closing remarks. It's not very difficult to generate electricity. The trick is to generate enough of it to drive something meaningful. This small generator can deliver enough to power lights or charge a phone, but that's about it. But it's also very small. If you want more power, simply scale it up. Beyond that, here are some optimization tips. Use stronger magnets. The stronger the magnets, the more bang for the buck. Wind bigger coils. The more copper you can get in there, the more electricity you'll get. Trade thin copper wire for more volts, thick wire for more amps. Add more gears. More gears mean more turns of the rotor equals more electricity. Of course, more gears will make it harder to drive the generator. Everything's a trade-off. Cut precision parts. 3D printed parts tend to warp and otherwise degrade. I deliberately made the parts flat, so if you have access to a laser cutter, you can cut the parts instead of printing them. Sadly, I don't have access to a laser cutter myself, but that would certainly be a tremendous efficiency upgrade. Minimize the thickness of the washer between the rotor and the stator. This brings the magnets of the rotor in closer contention with the stator, and that will substantially improve the amount of generated electricity. That will also make the rotor that much harder to spin, so once again, a trade-off. Everything in mechanical engineering is a trade-off, or indeed everything in life itself, if one gets philosophical about it. And that's it for now. I hope you gained something from this video. It's the first I ever made, so I certainly hope you did. Please give me a like if you think I should try and make some more videos, and subscribe so you'll be notified if ever I do more videos. Thank you for watching this. If you have questions, go ahead and post them and I'll try to answer as best I can. Check out the description for any updates or links to parts in relation with the project, and indeed the link to the TinkerCad design file. Happy tinkering yourself. Over and out.